We just saw that the statement not P or Q is not equivalent to the statement not P or not Q. Now, that might be disappointing to us if we're coming, for example, from algebra, where we can get rid of parentheses by distributing a negative sign. We might wonder, is there some way we can distribute that negative sign? Is there something without parentheses that this is equivalent to? And it will turn out that, in fact, that is the case. But what? How can we figure out what a statement is equivalent to? Well, let's start by just looking at a truth table for this statement. So to get a truth table for not P or Q, first we fill in the truth table for P or Q. Remember, or is true as long as at least one of the original statements is true. So true or true, that's true. True or false, that's true. False or true, that's true. And then false or false, they're both false, so the or is false. And then we negate that statement. So we'll look at this column and take the opposite of each truth value. Opposite of true is false. Opposite of true is false. Opposite of true is false. Opposite of false is true. Okay, so here's the statement that we're interested in, and we want to find an equivalent for it. Now, we're going to make a very similar move to what we did when we wanted to symbolize a statement. We notice that this statement that we're interested in, that we'd like to symbolize in some way, is true in one row of the truth table. And we're going to compare that to our just basic truth tables for our connectors. We see that there's only one statement that's true in one row, namely P and Q, the conjunction. And there's only one statement that's true in two rows, P if and only if Q, the biconditional. So if we want something that is true in one row, we need to find an and type statement, a conjunction. And it turns out that by using negations, we can control where that one line that's true ends up. Because there are four ways that we can combine negations and the and conjunction. We could have no negations at all and just have P and Q. We could have only P negated, so not P and Q. We could have only Q negated, so P and not Q. And we could have both statements negated, not P and not Q. And watch what happens when we do this. So P and Q, we'll want to look at these first two columns. So P and Q, both statements are true. And then when Q is false, the and statement is false. When P is false, the and statement is false. And when both the statements are false, the and statement is false. So here we got our true in the first row. For not P and Q, we'll want to look at the not P column and the Q column. Fortunately, and is symmetric, so we don't need to worry too much about what order these come in. So in the first row, not P is false, so the and is false. In the second row, both of them are false, so the and is false. In the third row, both of them are true. That's when and is true. And in the fourth row, the Q is false, so the AND is false. For P and not Q, well, now we want to look at the P column and the not Q column. So in the first row, not Q is false, so the AND is false. In the second row, they're both true, so that's where AND is true. In the third row, they're both false, so AND is false. In the fourth row, P is false, so AND is false. Then finally, for not P and not Q, well, we'll want to look at the not P column and the not Q column, and we'll AND those together. The first row, both of those are false, so AND is false. Here, not P is false, so AND is false. Not Q is false, so AND is false. And then here in the last row, both statements are true, so AND is true. And we notice that by doing this, we were able to get our true in whichever row we like. So no matter where we want to get our true, well, with the right combination of ands, we can get it in whatever row we need it in. We noticed this before when we were using truth tables to symbolize statements, but it's an important thing to note. It also helps us find equivalents. So in this example, we're looking for an equivalent to the statement not P or Q, which had the truth table false, 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 true, when we saw it above. And we see that that exactly matches this column. We see that the truth table we're looking for exactly matches the column not P and not Q, which gives us the fact that not P or Q is equivalent to not P and not Q. So this is not the distributive property, right? Because when we get rid of those parentheses, the or becomes an and. And that is one of two equivalences that have a name. The name of these two equivalences is DeMorgan's laws, for a mathematician named DeMorgan. This is the one we just found. If I negate an or statement, I get the and statement of the negations. And it turns out that it works the other way. If we negate an and statement, well, we get the or of the negations. And we just found the first version. The second version is one of the equivalences that you're going to demonstrate in the homework.